So this next chapter is titled Angles in Trigonometry. And in this first section, we're going to be talking about angles in particular. It's a pretty good straight line there. All right. So you guys, hopefully from your geometry class, remember you talked primarily about one way to measure angles. That one unit of measurement you used for angles in geometry was degrees, right? And most of us probably remember and feel quite comfortable talking about angles measured in degrees. There is, in fact, another way to measure angles that we're going to talk about right now. So it's funny you ask that. So we're going to start with this definition. So we say a central angle has a measure of 1 radian if it intercepts an arc with the same length as the radius. So this additional measurement that we're going to talk about for angles is called the radian. And the way that we've defined it is if we have a circle, when we say the central angle, we mean an angle whose vertex is at the center of the circle and whose arms intercept the exterior of the circle. So in our case, our central angle is this angle CAB. And what we're saying is that the measure of angle CAB equals 1 radian if the length AC, that's the radius, is congruent to the length of the arc BC. And remember, the way that we indicate something's an arc is we give it like an archy hat on it instead of like a straight segment hat. Yeah, that's why I'm making sure that I mention them as I'm drawing them. Yes, Mark? With the. So when we say the word congruent, we're talking about two things that have the same measure. So they might have both have the length of 5 centimeters or something. They can be. They're not always congruent. When they are congruent, we give that angle the definition 1 radian. So just like to be 1 degree, we might define it as, like 1/360th of the circle. Okay with that idea? So, good. The important takeaway here is that by this definition, basically what we're talking about when we talk about radian measure is we're defining that radian measure as basically the length of that arc when we embed this angle inside of a certain kind of circle, a certain size circle. Okay with that idea? So we have angles that we can measure with degrees and angles that we might measure in radians. A natural thing that we'd like is a way to convert back and forth between those two measurements. Right? If I have talking about feet and meters, I want a way to convert back and forth between feet and meters so I can compare the two measurements. I'd like the same thing to be able to convert back and forth between between radians and degrees so that I can compare the two measurements. So let's kind of build out a way to do that. So suppose that we have a circle, and let's say that this circle has a radius of 1. And the angle that I'm going to draw is this straight angle. How many degrees is this straight angle? Okay. And then what is this arc length here? So that would be the arc measure, not the arc length. It's pi. It is half the circumference of the circle. Remember that circumference is 2 pi r. So this circle has circumference of 2 pi. The green part is specifically half of the circle, so that is pi as a circumference. Everybody's okay with that idea? So what we have here then is 180 degrees is equal to pi radians. And that's our conversion factor. That's the key to kind of unlock translating back and forth between radians and degrees. So let's do a couple quick examples on how we do that, or of doing that maybe. It's not, we got the how answer right there. Yeah. So let's say we're asked to convert 90 degrees to radians. So just like if we were doing a unit conversion problem in your chemistry class or other science class, I'm going to start with the quantity I know. That's going to be 90 degrees. And then I'm going to multiply it by some conversion factor. The conversion factor we have is that 180 degrees is equal to pi radians. Which of those two things, the 180 degrees or the pi radians, should go in the denominator of this fraction? 180 degrees. Good. You should remember that the units should be on diagonals from each other. And then the numerator should be pi radians. So when I multiply across, I have 90 pi radians over 180. And when they reduce down, you get pi over 2. And frequently, when we represent radians, we like to represent them in terms of pi like this, when at all possible. So when you see something in terms of pi's, more than likely what's being described is going to be an angle measure in radians. So for example, if we're talking about a right angle, we could describe it as pi over 2 radians. It's the same as being 90 degrees. Everybody okay with that idea? Good. Let's do another. Let's say we want to convert 152 degrees to radians. So nothing really changes here, right? We'd approach this the same way. Everybody's okay with that? Now the reducing from 152 to 180, not quite as convenient, right? It would not be unreasonable in this situation, or in situations in general, for that angle measure to be preferred to be as a decimal rather than in terms of pi. So if I type in 152 pi divided by 180 into my calculator, I could also represent this as 2.653. And in terms of writing these, we can write the word radians afterwards, or more often than not, we'll omit doing that when it's clear from context what we're talking about is an angle measure in radians. Yes, Miguel? You got to remember that pi is there. So 152 times pi divided by 180. Remember, pi is basically 3, right? So 152 out of 180 is a little less than 1. 3 times a little less than 1 should be a little less than 3, which is what we're getting there, about 2.6. Okay with that?
So on the example above, the numbers just
Right. When we reduced, we can just reduce the 90 and the 180 to turn into pi over 2. Lindsay? I would, in the case here, I just rounded to 3 decimal places, mostly just because. In general, I would be specific on a test or quiz where I want you to round to. But here I just rounded to 3 decimal places, I think, throughout all of my examples, just to give us enough so that if you were following along on your calculator, you're like, okay, I see that I did that correctly. Right? If I just called that 2.7, it's a little more mysterious what I did to do that. Or perhaps, I don't know. But that's a fair question. If you're unsure on like a graded assessment or whatever, on if you've rounded enough, certainly ask. That's a perfectly reasonable question to ask and have answered. What if we want to go the other way? Convert 2 pi over 5 radians to degrees. Again, I'm going to start with what we know. I'm going to multiply by this, or multiply this by some conversion factor. What should be the denominator of this conversion factor? Pi radians, and the numerator then is 180 degrees. And when I multiply this out, I get 360 pi over 5 pi, which reduces down to 72 degrees. Now again, when we write radians, we can often give them to you in degrees, or I'm sorry, in terms of pi, or we can give them to you as a decimal. So instead of calling this a radian in terms of pi, maybe I just have 1.6 radians. Again, ostensibly, nothing's really going to change between this problem and the previous one. I'm still going to multiply by the conversion factor of 180 over pi. That gives me 288 over pi, which gives me about 91.673 degrees when I type that into my calculator. And again, I'm going to use those squiggly equal signs whenever I do any rounding there. So if you see the squiggly equal signs, that meant that I did some rounding from the answer on my calculator. Does everybody feel comfortable doing this? This should be pretty straightforward and quite easy, right? Okay. On to the next topic. So if a central angle that we're going to call theta, so this symbol here is the Greek letter theta. As an aside, oftentimes in trigonometry, we use the Greek letters to represent angle measures, and the standard A through Z letters to represent lengths. That's a common paradigm to use. Okay, so if we have some central angle theta measured in radians inside of a circle with radius r, then the length of the intercepted arc S is given by the formula S is equal to r times theta. How would this change if our angle was, instead of being measured in radians, what if our angle was measured in degrees? How would this formula change? Well, I'd have to convert this angle measure back to radians, right? So what do I do to do that? I multiply it by pi over 180. Or if I wanted to clean that up a little bit, maybe I call that pi r theta over 180 degrees. So this is just the same formula. All I'm doing is converting my angle measure in degrees back into radians so that I can use it in the previous formula, right? That's all we're saying there. So what's the trick to using this formula? Making sure you pick the correct version based on whether your angle is measured in radians or degrees. So let's do some examples here with this. So let's say we're asked to solve for S if r is 1.4 meters and theta is 0.98 radians. Which formula should I use, the first one or the second one? The first one, because my measurement is in radians. So when I plug in the 1.4 for r and the 0.98 for theta, I get 1.372 meters. That's pretty easy, right? Not too bad. What if we're asked to solve for S if r is 3.8 inches and theta is 40 degrees. We're going to use the second formula. Good. Because our angle measure here is in degrees. And when I do that, well, I get a log number anyways. It's not that terribly big. I get 2.653 inches. Everyone okay there? Okay. What if we're asked to solve for r if s is 18 centimeters and theta is 2.13 radians? Which formula should I use? The first one. And what do I have to be careful about here? Yeah, the variables that I'm given are a little bit different. Here I have to solve for r instead of s, but that's really not too big of a deal, right? So I just divide both sides by 2.13. If I do that, I get that r is 8.451 approximately. Yes, Sam. Of course. So let's look at a slightly more complicated example here. We're asked to find the perimeter of the sector with a central angle of 1.7 radians, cut from a circle with a radius of 5 centimeters. So a couple of vocab words to unpack here before it's clear what exactly it is that we need to do. The first word is perimeter. When we say perimeter, what are we really talking about? Just give me a really informal definition in words for what we mean by perimeter. Yeah, it's the distance around, or the sum of all the sides, or the perimeter is the all the the length of all the boundaries to the figure. Everybody okay with that? Okay. When we say sector, what shape are we talking about when we talk about a sector? It's not really a triangle. It's a pizza slice. Close. And when I say pizza slice, I'm not talking about one of these janky Jets pizza slices. I'm talking about a classical round pizza slice. That's just nonsense. Who's ordering a round pizza from Jets? Have you ever had a round pizza from Jets? You used to work at Jets. How many round pizzas did you make a day at Jets? Quite a few. So like one for every 20. I've never known anybody to order a round pizza from Jets. Yeah. All right. Shh. All right. Pizza time is pizza talk's now over. So when we talk about a sector, we're really talking about this figure ABC that's looks like a slice of pizza. Okay with that? So if I wanted the perimeter of sector ABC, how would I calculate that? What would I have to add up? Yeah, I'd have to add up the length of AB plus the length of BC plus the length of arc AC. Everybody agree with that in terms of how we'll find the perimeter? Okay. 2 of the 3 of those are really easy to calculate. Which 2 are easy to calculate? A, B, and BC. What are the lengths of A, B, and BC? 5. Because they're both radii of the circle. Everybody okay with that? How am I going to find the length of AC?
1.7.
I can use our previous formula, right? Remember that arc length AC is just a arc length of an intercepted arc. So that formula S equals R times theta would be appropriate here since theta is given in radians. I think I wrote theta times R, but you guys get the gist. Whatever is right. So that's 8.5. So the perimeter then is 18.5, and I think we measured these things in centimeters, so this will be in centimeters. Everybody feel comfortable with this? Again, not too difficult. We had a little bit of additional vocab to unpack, but it basically just came down to really using that same formula again. Thank you. So say a car has 18-inch diameter tires on it, and it's traveling at 15 miles per hour. And we're asked how many revolutions per second are the tires making? So we're asked for the revolutions per second. What kind of a quantity is revolutions per second? What's a rate, right? What word tells you that that quantity is a rate? Per. Are we given another rate in this problem? Yeah, 15 miles per hour is also a rate. So my goal here is going to be to convert miles per hour into revolutions per second. Everybody okay with that plan? Since they're both rates, I should be able to convert one rate into the other rate. So I'm going to start with the rate I know. So 15 miles over 1 hour. And I'm going to multiply this by some conversion factors until I'm in revolutions per second. Everybody okay with that plan? So let's start with the easy part here by converting hours into seconds. So how do I convert hours to seconds? So you're going to convert first hours into minutes, it sounds like. So I remember that these units have to be on diagonals from each other. So I should have 1 hour over 60 minutes. That'll cancel my hours. Now I'm in minutes. And then I'll have 1 minute over 60 seconds. That'll cancel my minutes, and I'm left with just seconds. Everybody okay to there? What's a little bit trickier now is to figure out how to convert this linear measurement of miles into revolutions. So let's think about what we're really asking to do here. Let's say that we have our tire here, and it's spinning in this direction. So when I start here and then end here, I want to know what that distance was to do like one revolution, right? Everybody's okay with that idea? I think the easiest way to do is to think about this visually. If I think about cutting my tire right here and then like unwrapping this end and laying it down here, what is that length really going to be? Yeah, that's one circumference. So I know that one circumference is going to equal one revolution. I know from geometry that the circumference of a circle is 2 pi r. In our case, the diameter of our tire is 18, so the radius is 9. So we're in 18 pi. And then since the tires were in inches, I know the circumference is in inches. So really what I need to do to go forward here is to convert miles into inches. And then I can apply this final conversion factor to get it into revolutions. So how should I convert miles to inches? Probably don't know how to go there directly, right? What would you want to do first? Miles. Let's do miles to feet first. Sure. How many feet are in 1 mile? 5,280 is correct. Good job remembering that. And then to convert feet into inches, I know 1 foot is 12 inches. And then I can apply that 18 pi inches is 1 revolution. Everybody okay with that? So to type this into my calculator, I'm just going to type it in as kind of one giant fraction. So I'm going to do alpha y equals to get that fraction command. And then I'm just going to type the tops all into the top of the fraction. So 15 times 1 times 1 times 5,280 times 12 times 1. And then on bottom I have 1 times 60 times 60 times 1 times 1 times 18 pi. Oh, goof. Look at what happened. I typed 6 instead of 60 there. I know, right? Goobered that up. Alright. So, you guys know how to do like second and then the delete key to insert something back in? Yeah. Oh, well, you learned something useful today then. Yes? Of course. So I got 4.669 revolutions per second. And I guess that's really an approximately. No! Alright. Everybody feel reasonably okay about these example problems? Not so bad, right? Mostly just kind of unit conversion like you've done in your science classes probably many, many times. So that's going to close section 1. That would be something I would probably tell you. Likely in a test setting, I would use like metric units there and just do like centimeters and kilometers or something so that you don't have to worry about it. Or you know the conversion because it's just 10 between everything. You know what I mean? Kind of helps remove the uncertainty there. Okay. So, in section 2, we're going to talk about trig functions of acute angles. Basically, that just means we're going back to our right triangle definitions from geometry. So if we're talking about angle theta, this side is the adjacent because one of the arms of the angle is that side. This side is the opposite because neither of the arms of our angle is that side. And this side is the hypotenuse because it's the longest side. So if I wanted to define sine theta, cosine theta, and tangent theta, what do I use? SOHCAHTOA. So sine is what? Opposite over hypotenuse. So SOH. Cosine is adjacent over hypotenuse, so that is CAH. And tangent is over adjacent, so that's TOA. Now these three, I assume that you are all quite familiar with. There are another three trigonometric ratios that we will talk about in this class in addition. They're referred to as the reciprocal ratios. So the first one is called cosecant, that we abbreviate as CSC, and it is hypotenuse over opposite. The second one is called secant, which we abbreviate as SEC, and secant theta is hypotenuse over adjacent. And the third one is called cotangent, which we abbreviate as COT, and it is adjacent over opposite. Any idea as to why we refer to those three as the reciprocal ones? Because they're literally the reciprocal of sine, cosine, or tangent, respectively. So the catch is, when trying to memorize these, is remembering which one is the reciprocal of which. The way that I always remembered it was that no cos go together. So cosecant shouldn't be going with cosine. Cotangent shouldn't be going with cosine. Secant and cosine go together. And if I can remember that one, the two with tangent and it go together, and that by elimination means sine and cosecant go together. That's the way I remembered it. I don't know if that helps you or not, but that's what I did. So let's do an example. So let's say we're asked to find all 6 of the trig ratios for this triangle in question. As I've currently drawn this, do I have enough information to complete this? I mean, so currently written down, I don't have all the information I need. There is some piece that I can find, though. Yeah. So I can use the Pythagorean theorem to find the third side of why did I write 6 there? That's just going to make life inconvenient. Let's make it 5. Well, this still doesn't give us a good round number, but I don't have to simplify the radical at least when I take the square root. So, square root of 40, I have to simplify the radical, and I don't want to do that right Fair enough. Now I have all the information I need to go on. So what is sine theta? Great. 5 over root 29. Are we going to leave that as our final answer? No. What should we do? Yeah, we're going to rationalize the denominator by multiplying it by root 29 over root 29, which gives us 5 square root 29 over 29. Everybody kind of remember doing that? It's been a minute, but that should refresh your memory there a bit. What is cosine of theta going to be? 2 over square root 29, but really we're going to write that as 2 square root 29 over 29, because we're going to rationalize the denominator again. I'm going to skip doing that when it's obvious of how to do it, showing the work anyways. Everybody's okay with me doing that? Good. This is the honors class. You should be. Good. And then tan of theta is 5 over 2. What's cosecant theta going to be? 5. Secant theta is going to be square root 29 over 2. And cotangent theta is going to be 2 over 5. Everybody happy with that? Again, that should be pretty easy, right? Okay. Let's look at another kind of problem we might ask you to be able to do. So, if we say theta is an acute angle in a right triangle, and sine theta equals 1/3, what are the trig ratios for the other 5? What should we do first in a situation like this? Yeah, let's draw a triangle. That's a little bit of a reductive answer there. I'm going to label this as side theta. And then we can fill in, let's see, I'll call these A, B, and C, some side lengths for this triangle now, right? What can we say here? CB is 1, CA is 3, and to find BA, what can I do? Yeah, Pythagorean theorem. So, got to make sure you put the hypotenuse in the right spot. So I get 2 root 2 for BA. Anybody issues with how I change square root 8 to 2 root 2? Good. Okay. So now, I just need to write down the values for cosine, tangent, cosecant, secant, and cotangent. What's my value for cosine? Squared, 2 over 3. What's my value for tangent? One over 2 square root 2. What do I need to do to rationalize this denominator? I just need to multiply by square root 2. You can multiply by 2 square root 2, but you have some reducing to do afterwards. When I do that, I just get square root 2 over 4. What is the value for cosecant? Two times the square root of 2 squared is 2 times 2. 3, right, is the value for cosecant, just the reciprocal of sine. What about secant? Yeah, 3 over 2 square root 2, which is 3 square root 2 over 4. And then my value for cotangent, 2 square root 2 over 1, or just 2 square root 2 is fine. Is everybody happy with this? Okay. Again, not terribly difficult, right? So finding exact values for trigonometric ratios is going to be something of special interest to us in the near future. The values of theta that we can find exact values for when theta is an acute angle are 30, 45, and 60. And the way we can find those exact values for sine, cosine, tangent, cosecant, secant, and cotangent are using our special right triangles. So if you remember the 45, 45, 90 triangle, has side length ratios of x, x, and x square root 2. And if I have a 30, 60, 90 triangle, the side lengths are, ratios are x squared 3, x, and then 2x. So if I use these, I can say like sine of 45 is, in this case, x over x square root 2, which reduces down to 1 over square root 2, which when we rationalize is just square root 2 over 2. Or for example, I could do cotangent of 30. Cotangent of 30 is adjacent over opposite, so that's x square root 3 over x, or just square root 3. So, in my opinion, these special right triangles are great things to have memorized. We will use them frequently. Will I require you to memorize them? I don't think so, but boy, I find them really pretty tremendously useful, and I refer back to them all the time. And if I were in your shoes, I would memorize them, because I would get a lot of use out of that. What about other measures of theta? What if I wanted to find out like sine of 17? How would I do that? Oops. Not really a trick question. Just going to use my calculator, right? That's our other tool. We can either find exact values right now, or we're going to have to use our calculator. Okay, so I'm going to just type into my calculator sine of 17. So I get about 0.29. What do we have to be careful about when doing something like this? Your mode. Your calculator mode is going to matter a lot. To do sine of 17, what mode should my calculator be in? Degree. So if I press the mode button and check, let's just see what happens if my calculator was in radian mode and I tried to do this. I get this. Does this number make any sense? What? Yeah, the negative makes no sense in this situation, right? If we're talking about side lengths in a right triangle, negative makes 0 sense. The number one mistake students make in this course is not having their calculator in the right mode. It is a devastating mistake. Please, please, please be careful. And there will be places on the test where you're going to have to be converting back and you're changing back and forth. Because there'll be problems in degrees, there'll be problems in radians, and they'll be mixed up, where you're going to have to remember to change your calculator mode back and forth. I want you to make sure when you're looking at a final answer in this course, you need to think about, does this make any sense at all? And if you're trying to tell me that the side length of a triangle is negative, I need you to go back and think about that one again. Okay? That is an important distinction and an important mistake that I do not want to see you guys make. So we do have to be very careful about our calculator mode. I have one more example problem to show you, and then I am going to call it quits for the day. So the last example problem says to solve the triangle. When we give the instruction solve the triangle, what are we really asking for? Good. To find all the angle measures and all of the side lengths. What's the easiest thing to find here to start? The other angle. How do I find that other angle? Right? I can find it by just taking 180 minus 41 minus 90, or just 90 minus 41. Either one is okay. So I can see that that's 49 degrees. Didn't have to do anything tricky there, right? Okay. Let's find one of these other two side lengths. Does anyone have a preference on which side length to use or to find? Okay, you want to find this side then? I'm going to call this X. Next we need to pick an angle to use. Which angle would you like to use? The 41. So relative to 41, we're looking for the opposite side, and we know the adjacent side. Which trig function should I use? Tangent, because tangent is opposite over adjacent. So to solve for x, I can just multiply both and get that x is 12 times tan 41. So if I do that and type in 12 times tan 41 and press enter, does this answer make sense? It is awfully small, right? If I look at this angle, it's 49. That side length is 12. This is only a little smaller angle, but I got a massively smaller answer. What do you think is wrong here? I'm in the wrong mode. Remember, I changed it back to radian mode to show you guys what would happen. I didn't change it back to degree mode. I didn't goof on purpose or on accident. That was absolutely on purpose, because that is the kind of mistake that students make all the time. Please make sure you're being careful. Once I find this side, we have one more side to find. How can I find that third side? Okay? You could use the Pythagorean theorem. Is that the best way to do it? Is it the most accurate way to do it? No. Why not? Because you have to use another rounded answer to get that answer. Is there a way to do this without having to use any rounded answers? Yes. I can do, for example, cosine of 41, which is 12 over x. If I multiply both sides by x, and then divide by cosine 41, I would get my other answer, and that will be marginally more accurate than if I had done the Pythagorean theorem. Not tremendously more accurate, but it will absolutely be a more accurate answer. Just to illustrate how much more accurate, if I do 12 squared, actually, let's do the square root of 12 squared plus, and then I'll take my rounded answer that I got before, 10.431 squared. You notice that it is a little bit different, right? Now, depending on if you're rounding to like the 10th spot, probably doesn't matter much. If you're trying to launch a rocket and land on the moon, it probably matters a lot. So, depending on the context, we have to be a little bit careful about that.